Hi everyone, we're going to show you how to fit some standard reference material data collected from the Nomad instrument. So this is the program PDFgui. There's a reference for it here. We have more information on everything I'm going to show you in a document that you can find posted with this video. I'm just going to show you how you start a fit in this program. Say new fit. Give the fit a name. You then need to select a phase, a structural model for your material. I have a crystallographic information file that I can load in, just like I showed you. You can see that when you load a structure file in this way, it automatically expands the space group out to all 8 atoms in the unit cell. The one thing I have to do here, this is a common problem you may encounter with this program, is it will parse the element number exactly how it's written in the file. This program doesn't know what Si0 plus is, so I'm going to replace that with Si, silicon. So I have a structure file here with atom positions, isotropic atomic displacement parameters where all 3 of these are equal and they're all the same starting values. I have lattice, A, B, and C all equal. It's a cubic system. One thing I need to do here is put a guess or starting value under this configure tab for either delta 1 or delta 2. These guys are the correlated parameter values. Good guess is something like 2 or 3 for, say, delta 2. This is a 1 over r squared dependent correlated motion peak sharpening parameter. Okay, so we have a phase inserted. Now I'm going to add some data. I want to add silicon SRM 640E. I want the file with extension FTFRGR. This is the big G of R that we typically fit in the PDFgui program. There's also more information about that available on the Nomad webpage and different file extensions. And the header, the metadata in the file had the data range was read in, the Q maximum was read in, and then some good guess starting values for the Q damp. This is the instrument dampening in real space, and Q broad. This is the real space broadening as a function of R for the instrument. And what we're doing here actually in fitting this standard reference material is finding accurate updated values for Q damp and Q broad based on the instrument characteristics of this run cycle. So I've loaded in my data, which is great. What I need to do before I start fitting is choose a data range. That's selected here in fit range. I'm going to start with something like 1 to 20. And then I need to add constraints for this refinement. And there are constraints for both data sets and for structure files. So under the data set, the constraints I have access to are for the scale factor, the Q damp, and Q broad. And the constraints I have access to for the phase are all these different structure parameters. So for sure, we need to refine the lattice parameter. I'm going to give what we call a handle to that variable. I'm going to use @ to say this is a handle for the parameter, and then you give it a number, a unique number. Now when I use the same number in different boxes here, I'm actually constraining these 3 parameters to be equivalent. So I now have constrained A to equal B to equal C. I've configured a starting or guess value of 5.43053. So when this refines, all 3 of those parameters will refine together. We'll also need a scale factor for the data set. And if you remember, there's both a scale factor under the data and a scale factor under the scale. You could use one or the other. They do the same thing during refinement. However, if you have two data sets, you'd want to use separate scale factors for your two data sets, and then have a unique one for the structure file. And if you had more than one phase, you'd need scale factors for the two phases as well as one for the data set. But only use one if you have one data set and one structure or phase. Then I need to put in one of these correlated motion parameters. I'm going to give this an @2 distinction or parameter handle. And but these values can be anything. I could use @200 if I wanted to, or @35. It just has to be a unique number I haven't used anywhere else. And there are no special positions in this space group, so everything is a fixed atomic coordinate, so I do not need any constraints in X, Y, and Z for this phase. However, I do want to add a atomic displacement parameter refinement. I'm going to do @20 for that. So now I've made the U11, U22, and U33 variables equivalent for each silicon atom here. So at this point I have excuse me. At this point I have given constraints for all the parameters I need to refine the low R PDF in this case. So I'm going to do an initial refinement between 1 and 20 angstroms. The way I do that is I highlight the top of this fit and I click this little gear to start the fitter calculation. I can see that I've got a final agreement factor RW of something like 6.7%. Sounds pretty good. If we want to look at it, we can highlight this data set and push this little plot PDF or structure. This shows me my refinement as a function of real space. It looks pretty good over the range. So if I want to change where this difference curve, so I have data in blue, our calculated fit in red, and a difference curve in green below. If I want to see that falling below the data, I can change my offset here to something like -12. And then when I replot this, you'll see the fit difference below. Okay. Now what we're going to do is copy refined values. So I highlight all these and right click, copy refined to initial. I'm going to do this refinement again, starting from now better initial parameter values. So there we go. Basically have very stable results here. So I'm happy with this refinement. Now I'm going to copy this fit and change the range. I'm going to do a 50 angstrom fit for this data. So if I want to change the range, I need to go to the data set under the configure tab, and I'll now change this to be 1 to 50. It knows I don't have any data beyond 49.99, so the program actually makes that my highest R value. And now what the purpose of fitting this data set here is actually to produce the QDamp and QBroad parameters. So I need to add those as values to refine. So I put handles here. I'm going to use 100 and 120. And now if I go to the top level of the fit under parameters, I see these two new parameters. What I'm going to do is I'm going to fix the QBroad term and refine the QDamp term first. And I push start. And this takes considerably longer because we have a much wider R range to calculate the pattern and compare the pattern over. So I'm going to do this copy my refined parameters to initial parameters. I can take a look at this. You can sort of see, the trained eye can actually see that I have a little bit higher misfit in this range than I do in this initial one. And I think that will improve when we add this last QBroad parameter into our refinement. So again, I'm going to go to the parameter link. I'm going to unfix that last QBroad parameter. That's our handle 120 in this refinement. And I'm going to repeat this again. So what we're doing here is finding out the instrument broadening and damping given a crystalline material that has no disorder. So that when we go ahead and study materials that have some intrinsic disorder and maybe dampening and broadening due to their structure, we've taken care of all the instrument effects. So at this point, we've completed this standard reference material PDF refinement between 1 and 50 angstroms in real space, and we've generated values for QDamp of 0.020 and QBroad of 0.0185. And when we go study research material we don't know everything about, then we'll set those parameters. We'll do that in another exercise. Thank you very much for listening.